Okay, let's talk a little bit more about security. So let's really talk a little bit about protecting systems and so on. So, attacks on computer systems. Most of the attacks that we see executed against computer systems fall into a couple of categories. So first of all, we have software implementation faults. Now, we could really, if we thought about this, we could, and I'm just going to find another color to write with here. If we thought about this, we could really say this was programming errors, we could also say this was vulnerabilities. And we could also say that this could either be intentional or it could be unintentional. Oops. So implementation faults, or what we would say buffer overflow attacks. Generally, what we're looking at here is something along the line of, let's say we have a program in memory. So here's a program in the computer's memory. And programs tend to have three sections to them. We have what we call a stack segment. We have something called a data segment. And we have something called a code segment. Now, what's really the example I'm going to give you here is very, very straightforward. The stack segment is used to store temporary values. So these be temporary values used by the CPU. Now, long strings of data get stored in the data segment. And of course, executable code is going to be stored in the code segment. So if a program, for example, wouldn't actually test an input, we could say maybe that somebody sending data to say a web server over the internet sends an extra long packet of data. So this packet of data actually overwrites into the stack segment of the program. And then by doing that, assuming that the attacker knows exactly what type of web server is being used, they can change values in the stack segment. And then they can affect the way the web server actually is going to operate. So they could, for example, cause it to execute another copy of itself or open up a shell so that they could then have command line access to the server, all kinds of things like that. Sometimes overflow errors are just if you typed too much in from a keyboard or into a login prompt, you might be able to cause the computer to fail. Protocol failure. Now, we see a lot of this with TCP/IP is just an example. Whereas the protocol was never intended to be secure. So we could say TCP/IP as an example. Never designed to be secure. So that means that it's open to things like session hijacking or masquerade attacks, that type of thing. And of course, password guesses. So password guesses largely caused by dictionary attacks. So we could say dictionary attacks. That's generally bots or programs that run on the internet and are doing this type of an attack. So your textbook lists a bunch of vulnerabilities. Vast majority of internet-based attacks are worms, SYN flooding. SYN flooding is the idea where a TCP/IP packet, so let's just take a look here and see if I can shrink this page down. So we have a packet. So here's a TCP/IP packet. And the packet has a header. And then it has the payload. So we'll just write that in here, the payload or the data. And in the header, there's a section for what we call status bits. And one of these is the SYN bit, which is for synchronize. And now what that actually means is that if the SYN bit is set, then the internet, the network connection is actually going to sort of reset itself so that the packets are synchronized. This ties up resources because there's a lot of network traffic that's generated and it takes up CPU resources and so on. So it's sort of a form of a denial of service attack. So we could also say that this is a DOS attack. Then, of course, we get something called a distributed denial of service attack. And with a distributed denial of service attack, what we're going to have is we'll draw the internet here as a cloud. And we're going to have a victim computer. So this is a server on the internet. And then out here, we're going to have a bunch of computers that have been taken over by malicious software. So they've all become members of a botnet. And there could be hundreds of them. These little square tic tacs here, these are the keyboards. So we're going to list these as a botnet. And they're all going to send packets, connection packets, to this server. And the idea is that the server becomes flooded with connection requests. So viruses, generally, when we look at viruses, what we're talking about is malicious software. And malicious software is generally any software that's going to cause the computer to work in a way that wasn't really desired by the operator or by the owner. Now we could say that about a lot of websites that generate pop-ups and all that kind of thing. Some are malicious, some are for commercial purposes. So there's a whole gamut of software that personally I see that falls into this malicious category. Whether it's legal or not is somewhat beside the point. If the computer is operating in a way that's annoying, for example, you go to a website and it generates like 3 or 4 pop-ups, then you could consider that malicious behavior. Generally, the criteria for a virus are, first of all, it infects a host. A host. And when I say host, what I'm really talking about is a program. So a virus generally finds a program that it can infect and insert its malicious code. The other thing that a virus does is it replicates. So it makes copies of itself. So for our purposes, computer virus refers to any code that causes computer or network systems to behave in a manner other than was intended. So something I didn't list above is the objective. So the objective could be nothing more than to infect a program in the simplest case. In a more extreme case, it could cause the computer to operate strange. One of the codes that we experimented with back when I was in university was we wrote a program that infected a Windows system. And what it did was the faster you typed, the more errors it introduced to your typing. So if you were typing nice and slow, no errors. But as you sped up and you typed faster, it would start inserting random errors into what you were typing. So that's an example of an objective Some viruses obviously have other objectives to, for example, exfiltrate data or to steal credit card information or any number of other things, passwords, bank account information, all can be objectives of a virus. So viruses will search for other programs to infect, and then they're going to insert hidden instructions. So this is kind of an interesting idea. So we have a program in memory, and the virus comes along, and maybe it replaces some of the code with its own code. The other thing it could do is it could append malicious code onto the executable. Now, there's some indicators that this type of thing has happened. So, for example, the file has a different length. Than what it's supposed to. Or it has a different checksum. Put little bullet points here. It could have a different MD5 sum. I say could, but should say that will change, and so on. So the execution sequence of the program is going to be changed. In other words, the execution path, the path that the CPU takes as it executes the code, is going to change. And the hidden code, or the malicious code, is going to execute any time that the program is invoked or any time the program is run. Generally, it's an event or a something that happens that's going to cause the virus to execute. So it could be a key press. It could be a connection to a certain website. It could be any number of things that the people who've programmed the virus, that they've caused it to look for, and which actually act as triggers. And when a virus executes, so we're going to say here, when it executes, that is when it dumps its payload. And the payload is whatever the virus was supposed to do. It's whatever action that virus was supposed to do. Lots of ways that we can detect viruses. So we could look for a virus signature. So if we were to take a piece of code, a little snippet, and then we took another little snippet out of a piece of code, and then we took another little snippet out of that same piece of code, and we took these distributed through the program. So we don't take them all in one stretch. We take them with some space in between them. So there's a number of bytes between each of these snippets. We do this on purpose because, oops, we do this on purpose. So let's say executable. And the reason is that if we take all of our little snippets of code in one place, there's more chance of false positives. In other words, it could just be an ordinary program, and it's gonna trigger as being malicious. So what we do is we take these spaced out throughout the code, and that means we get a different sampling, like a more accurate sampling of the code. So when we have a signature and we then compare that with a piece of code, so let's say, whoops, how is that happening? We compare that with a piece of code in an executable. Oops. Let's do this again. We stand a much better chance of getting either a true positive or a true rejection rate. So we can do things, other things. We can use artificial intelligence. We can use machine learning. We can watch for the behaviors of programs. We have what we call A-plane and C-plane analysis, where we look at the network activity versus the calls to the operating system. Different things that we can do in order to detect viruses. And we can be proactive. That is, that we, as code or as information comes into the computer, so then we examine it. Active detection. This is your average virus scanner, which is always running, and it measures everything to see whether or not it's malicious, generally using a signature type approach. The issue with this is that it generally bogs down a lot of CPU cycles, so it will definitely affect the performance of the computer. Then, of course, we have reactive, which is we worry about doing something after the problem. So we're reacting to the problem or after the event. So proactive, active, and reactive. So several different types of techniques. So signature scanning, which I just described using some type of an algorithm. A general purpose monitor. Now, this would be generally something like Tripwire. So you can look at tripwire.com or tripwire.org. Access control shells. In other words, we could use some type of a reference monitor that examines exactly what the computer is doing all the time. Checksums. So a checksum is essentially a value that is calculated against a piece of code. And if it changes, then we have a problem. And heuristic binary analysis, this is generally using rules of thumb. In other words, we watch the behavior of the program. So DDoS attacks, and I've already described a DDoS attack. These happen a lot, distributed denial of service attack. So that's what DDoS stands for. And in this case, we're going to have a whole bunch of infected computers. And they're all going to be under the control of a bot master or a bot herder. And they're just going to all perform a very targeted attack against the server. And generally the bot herder is going to operate through what we call a CNC server. And a CNC server is a command and control server. Intrusion detection. Now we can talk about this, and we usually abbreviate this as IDS, which is short for Intrusion Detection System. And we have two types. We have host-based, and that could be a virus scanner, tripwire, etc. And a good example of a network-based IDS, and the very best one that I have come across is called Snort. And you find that at snort.org. And what it does is it monitors your network and it watches for anomalous activity. Firewalls. Firewalls are essentially hardware. Sometimes you'll have software firewalls. And really what they are is they're big network filters. They use the contents of packets to decide whether or not to let a packet through. And there are all kinds of attacks that can be executed against firewalls. Generally, the idea is to exploit the rule set of the firewall. Generally, it uses data from the header. And that header data, so source IP, destination IP from the packet, what bits are set, different as far as the control bits and so on, and the status bits are all used in conjunction with each other to determine whether or not a packet's allowed through the firewall. So we'll look at a couple of different scenarios here. So the first one is what we call a packet filtering firewall. Now, in this case, we're just using your generic Cisco router. And behind that router, so in front of it, we have the internet. So we have clients. They're connecting to the router. And behind the router, we have our important servers. All the router does is it looks at source and destination, IPs, control bits, and that type of information to determine whether or not a packet should be allowed through the firewall and whether or not it should be allowed to connect to one of these servers. So that is your simplest case, what we call a packet filtering firewall. Next level of complexity is something we call a bastion host. Now, if you look at this scenario is exactly the same as a packet filtering firewall. The only difference is the addition of the bastion host. Now, you probably would like to know, what is a bastion host? And a bastion host is a computer with two or more, with greater than or equal to two network cards. And it can be used to filter the packets in ways that the Cisco router won't. So all this does is adds another layer of protection. Then we get our DMZ. And a DMZ is a demilitarized zone. And what do we do here? We insert a second Cisco router. So we've got a Cisco router here, and we've got a Cisco router here, and then our bastion host sits in between. So our bastion host could also be used as a honeypot. In other words, the Bastion host could be made to look like a target. So any attacker on the outside attacks the Bastion host instead of attacking the valuable servers, the valuable legitimate servers. And when we do that, we call it a proxy server. So you notice the topology here in the DMZ and the topology with a proxy server are absolutely the same thing. And what the proxy server does is it acts as an intermediary server, and all the data can be passed through the proxy server. In other words, the proxy server could look like a web server, or it could look like an FTP server or an FTP client, so that all the communications, either side, is taking place through the proxy server. So we would have all of our incoming connections connecting to our proxy server, and the same thing with all of our outgoing connections. And so if an attack occurs, then it's going to be the proxy server that gets banged and not the actual really valuable servers. The only thing we have to reconstruct is the proxy server. So as far as operating systems are concerned, always try and use the most current release. And keep them up to date. So run your updates, make sure your operating system is up to date. Make sure that you harden the operating system so you can shut off processes that you aren't using, things like that, so that you have less running on the server. The more streamlined you make your server, the less of an attack surface you have. You can install things like TCP wrappers, use an intrusion detection tool. Snort is a really good example. You can, and you should, instead of Telnet or FTP, you should use encrypted connections. So you could use Secure Shell. SSH is Secure Shell for remote connections. And for FTP, you want to use Secure FTP or SFTP. So these two should generally just have a red line through them, because these are what you want to use. You can do penetration testing. So there is software available. I give you a link here for Nessus, and it tests each port to determine what's open, what's listening, and so on. Now, IPsec is sort of designed to give a little bit of security to the TCP/IP protocol suite. So the problem is that an attacker can easily forge IP packets or the addresses, or replay old packets. The other thing that can be done is using a program such as Wireshark. It's possible to look at the contents of packets, perform traffic analysis attacks, as in where are packets going, where are they coming from, what is the frequency of those packets, when's traffic heaviest, all these types of things. So we want to try and build a little bit of security into the TCP/IP protocol suite. So IPsec essentially is a system where the packets can be encrypted. Now, the thing that we have to remember is that in this scenario, what we actually have is encrypted data. So the actual data is encrypted. Meanwhile, our header is not encrypted. So what I'm trying to tell you is this is very much like the scenario when you connect to your bank's website. So you log in, your username, your password are encrypted. The communications between your computer and the bank's computer are encrypted on the level that nobody can read the data. But it's entirely easy to tell that you're connecting to your bank's website and that you're obviously doing banking. So the contents is encrypted, but the method of connection is not encrypted. And it can be read by an outside party. So IPsec is really intended to try and protect the datagrams. And the idea would be to have the ideal scenario would be to get rid of TCP/IP altogether and use an encrypted system where everything is encrypted. Now, a good example of this is something we call Tor. That is the Onion router, where the packets are bounced around inside an encrypted network to make it harder for somebody to be able to trace where the connection is coming from, where it's going, or to read the contents. And if you look at if you Google on this, they have some very good explanations on their website. So IPsec, not secure. So we have an application. The application is going to generate data. That data is going to be moderated by the TCP/IP protocols. With IPsec, we have some security over the routing protocols. And that's really what this is all about. Here, there's no security. In other words, the headers are not encrypted. Here, our headers are encrypted, and there is some means of disguising the source destinations of the packets. So if we can add SSL, so you connect to a bank's website. So you connect to a regular website and you've got plain text. Running over TCP IP. And with a more secure protocol, you've got SSL. So the HTTP, which is actually just the protocol that's being used to connect to a web server, this data is encrypted. So that's really what's going on here. And even if somebody can trace where your packets, your source and destinations of your packets, the data itself is still encrypted. And we've got other protocols, so encrypted message syntax is a part of the MIME suite, and RSA uses something called public key cryptography. And it sort of works like this. We have two types of cryptography. So let's say crypto, two types. Symmetric and asymmetric. Symmetric uses the same password or I should say key, to both encrypt and decrypt the data. In other words, if you get the encryption key, you've also got the decryption key. This is much, much simpler. Simpler and less secure. Here, we have two keys. There's an encryption key and there's a decryption key. And generally this uses something we call PKS or PKI. I'll use PKI, and that is the public key infrastructure. Okay, a VPN. Oops, let's just go back here. Just to recapitulate on this or recap this. Asymmetric, because it's using two keys and because of the use of the public key infrastructure, is much more secure than the symmetric. It's asymmetric encryption is what's used when you connect to your bank. And this is used in the RSA algorithm, which is based on prime factors of extremely large numbers, which is where the protocol actually gets its security from, because it's very, very impossible to guess the prime factors of these extremely large numbers. VPN is a way of simulating a private network. And we see this today. VPNs are really in quite common use. VPNs are being used by people who are downloading movies. There's any number of companies out there offering VPN services where there's a subscription service, and essentially all you're going to do is subscribe to the service, and then your IP, your identity is protected over the network. Your traffic is encrypted. Your location is hidden. There are a lot of different services. The one that just comes to my mind is called Express VPN, and you can Google on this if you want. And that will give you essentially a really good idea of how a VPN works. Now, the idea historically comes from the idea of being able to tunnel through a public network, which is the way this is still working. Essentially, it just creates an encrypted tunnel in a regular network, and this causes the traffic not to be trackable on the regular network. The traffic can be seen, but it's not really trackable. Now, if a private person is connecting to a VPN, anybody observing their traffic from the outside can definitely tell that the host is connecting to a VPN network, particularly if they can tell what IP address is being connected to. So here's the way it works. Here's a person. Here is a person, a host. The host is going to connect to a VPN server. Pardon my artwork. Maybe I should exercise a little bit more care with my artwork. So here is the VPN server. And now the VPN server is now going to act like a proxy. So whenever this person, so we'll say call this person Alice. Whenever Alice is connecting to websites or other servers, her traffic runs through the VPN server, and the VPN server obfuscates the fact that it's her. Now, these services will have VPN servers all over the world. The user has a little program they run on their computer, VPN client, and the VPN client will connect to any of a list of known servers around the world. So if an external entity who's observing the network traffic has the list of the IP addresses for the VPN servers that are around the world, then it's easy to tell that Alice is connecting to a VPN server. The part that's not easy is that after she's connected to the VPN server, it's very difficult to connect to determine what she's doing, what websites she's browsing, if she's downloading programs or downloading movies, or if she's communicating with secret friends or selling the Colonel's secret recipe, whatever she happens to be doing, this is the part that becomes obfuscated. So that is the end of our lecture. So hope you enjoyed it, and I will see you in the next video.